Okay, this lecture is going to be on dimensional analysis and similarity. Last class we went through and was able to calculate the force of lift knowing the coefficient of lift and some information about our flow regime, velocity, density, and as well as the size of our wing or our profile that we have. That was just going to be, or that was an introduction to the use of a much larger topic, which is dimensional analysis and similarity. What dimensional analysis and similarity allow is if you're able to come up with a coefficient of lift, you can allow you to make comparisons between models, which are going to be small, easy, manageable sizes, and prototypes, which are going to be the real physical airplane that you would want to build, or a real physical size of whatever the model is to represent. Now there's going to be important things, or there are important parts, of the dimensional analysis and similarity, which we're going to go into. We're just going to briefly touch upon some of the power and ability and flexibility that dimensional analysis has. The use of dimensional analysis is that it's much easier to work with a model that represents all the important geometry that the prototype or the real physical apparatus that you want to use, an airplane or a submarine, that's going to be represented into the different non-dimensional coefficients and numbers. So, continuing with where we left off last time, we worked with lift. From last time we had the formula for force of lift in terms of coefficient of lift multiplied by this quantity. However, now we want to define the coefficient of lift as the force of lift divided by 1/2 rho v squared and the important area of your model as well as your prototype. This is going to be a result of dimensional analysis and similarity. So this will be the end result. So this is the final result, but to get to this, a more general process and procedure is needed. So let's start with what we do know. We know force. Force is going to be represented as a function the important parameters that you can think of that are going to be fundamentally different between any particular shape and any particular flow regime that's going to affect force is going to be a function of density of the fluid, the length of your geometry or prototype or model, whatever you have, or the shape, the viscosity of the fluid, and the velocity at which the fluid or object is moving within the fluid. So L is length measured in meters. Velocity is meters per second. Rho is density, kilograms per meter cubed. And mu is going to be dynamic viscosity, which is a Pascal times a second. So in general, a force is going to be dependent on those parameters. Flow parts as well as your model or your prototype. There's going to be some sort of function. Function is just going to be some sort of mathematical model. But the issue is coming up with what that mathematical model needs to be. So, dimensional analysis. Why do you really need this? Because you can just go and do the complex analysis and come up with an answer. But there are two important reasons to do a dimensional analysis. So we do a dimensional analysis to reduce the number of variables. With the reduction of the number of variables, allows anyone to save time and money. The reduction of time, we'll get to the reasons. If you have to vary all these different, if you have to adjust all these different variables to come up with a function for force, and you vary each one, that's going to be a lot of different experimental runs you'll need to do. As well as, for each one of those particular fluid properties, you have to come up with and purchase those materials. In addition, you have to spend all that time, which also time is money because you have to pay someone or you have to perform those experiments and take the data. Okay. Also, the dimensional analysis allows one to focus on the important variables, and it allows you to remove extraneous variables. You can go through the mathematics and find that maybe there's a function, but sometimes, or a function of a particular variable that you would think would be important, but going through dimensional analysis allows you to remove extraneous variables. What that allows is a very concise, easy way to represent the data. So, well, let's just talk about this a little bit. So if you have force as a function of density, you would think that as you increase the density, force is going to go up. So that can be represented as a line like that. Linear line, very, very simple. But what happens to length? Well, you could also have force as a function of length, and that also might increase that you would have. For an increasing length, the force would also go up as well. However, what is the effect if you increase the density and you increase the length? Now you would have to have a three-dimensional plot. So force would go up, and then you would need to have another axis to take care of density and length, and then you would have a contour plot of by varying these variables to have the representation of force. What would happen if you have a third parameter and a fourth parameter? You have a very, very complex representation of the data. And then again, that just grows because for each length you got to keep adjusting the density. Then you adjust the density and you have to keep adjusting the length. You have a lot of experimental runs to get the representation of force. So it allows you to have nice, easy, concise way to represent the data. It allows you to scale from a model, something very easy to handle, easy to do experiments on, to scale from the model to the prototype. So the actual size of an airplane is rather large. So to work with a large prototype and to get the flow regime that's going to be needed, you go through and build a prototype, but it might not actually fly. So the first goal, or the first step, is to build a model and then scale it up. So models are smaller models are generally smaller than the prototype, generally less expensive to build, less material, less detail you need to put, or less ability to make that model, and easier to have your experiments on. Now if you have something that's very, very tiny, building something at a much, much smaller scale, it's going to be difficult to actually perform experiments on, so you can make a little bit larger model and then scale down. So it works in both. From the model is generally something that's small that we can handle, humans can handle. But the prototype can be larger, or the prototype can actually be smaller. But the prototype is the actual size, bigger or smaller. The model is something that humans can easily handle. Less to produce, easy to perform experiments on. That is the power of dimensional analysis. So as we stated here, force is a function of 4 variables: density, length, viscosity, and velocity of the flow, or the velocity of the object in the fluid. So if you're going to perform an experiment, so typical data to come up with how force is related to density. Generally you would want to come up with and perform 5 to 15 experiments for different densities, different density fluids, to come up with how the force responds to changes in the density. But again, as pointed out, if you wanted to do the same thing for length, from 5 to 15. And viscosities from 5 to 15. And flow regime velocities from 5 to 15. You're going to come up with a lot of different experiments. So have to perform the experiment for 15 different viscosities. Then within that, then you need to perform the experiment with 15 different densities for each one of the viscosities. Then (15 different velocities for each of the 15 different densities for each 15 different viscosities. And then finally the same thing for the lengths. So what this equates to is 15 times 15 times 15 times 15, or 15 to the fourth, a negative fourth, which would be 50,625 experiments would need to be run, not only to try to find all these different parameters to perform your experiments, or at least different, well, I won't go into all that particular detail how you can get different values, but to get a good understanding of the force in terms of all these different variables, you have to perform a lot of experiments. The issues. So, again, as previously stated, the issues are you have an enormous amount of time would have to invest to perform all those experiments. An enormous amount of money to perform all those experiments. And then after you do, or if you chose to perform all those experiments, how are you going to organize the data in a useful manner to pull out or get some sort of representation of how to use it? Again, this is where dimensional analysis and similarity come into play. So, force is a function of density, length, viscosity, and velocity. We can rewrite this representation as the force divided by now. There's a lot of mathematics, or well, not too much mathematics, but again, it's beyond the scope of this class of how to come up with this representation. But it is seen that if you take the force and divide it by the density, the velocity squared, and a length squared, it collapses nicely to a different function. We're going to call that function g, where g is just a function of Reynolds number. If you can remember back, that was a very important non-dimensional number that was initiated in the beginning, or described in the beginning of this class. Reynolds number is a very, very important dimensionless number. So, taking the force, dividing it by the density of the fluid, the velocity squared of the fluid, and the length squared, or an area of whatever is the solid model that you have. Again, that could be a wing, an airplane, or a submarine in a different liquid. Anything that is going to be moving in a fluid, the force that's on it divided by this density, velocity squared, length squared, can collapse all of the functional results as a function of simply Reynolds number. Again, it's beyond the scope of this class, the process to do that, but if you want to research and learn the process, this process is going to be the Buckingham Pi theorem. Again, it's beyond the scope of this class, but there is a way to take this function, collapse it down, where if you vary Reynolds number, you can get a nice representation of data as a function of just Reynolds number. And technically, if we're talking about an airfoil or an airplane, the angle of attack, alpha. So, since that's what we originally introduced, the angle of attack is going to be an important parameter that we can vary. So, going back to this, we have an extra 1/2, which is not in here, but that's for some easy way to model the data. And again, area, the important area that you would have would be where the force of lift is going to be applied, or the stress going in this direction, perpendicular to the plane, is going to be your length squared. So changing length squared to an area, some sort of squared length in the x and maybe in the y, that is, can be considered a length squared, and throwing a 1/2 in there, we can get that to be that representation. It's just a constant. 1/2 is just a constant. So now we can say the coefficient of lift is really going to be some g function of Reynolds number and alpha. Coefficient of lift is just a function, some sort of mathematical representation that varies as Reynolds number and angle of attack. And we went over Reynolds number, rho v L divided by viscosity, and angle of attack, how the area of your wing is represented into the flow. So the flow is going in completely parallel with the ground. Angle of attack can be varied, and again your coefficient of lift will change. And it will change generally as Reynolds number. Now, whether or not if it's highly sensitive or not sensitive, that's another exploration that will need to be investigated. So, Buckingham Pi theorem allows you to investigate physical phenomena, forces,